This video focuses on mechanistic and a few practical aspects of making aldehydes and ketones by the oxidation of alcohols. It's appropriate for second year organic and biological chemistry module. So this is the transformation we're going to focus on in this video. We're going from alcohols at oxidation level 1 up to aldehydes and ketones at oxidation level 2. There are a multitude of reactions that go beyond oxidation level 2 up to carboxylic acids and the like, but we'll deal with those in lectures and problem sessions. Also, for the purposes of this video, I've stuck with primary alcohols going to aldehydes, but all of these protocols are equally suited to oxidizing secondary alcohols up to ketones. I just haven't shown them as examples. So we're going to start off with a general mechanism. We're going to introduce this general oxidizing agent shown in orange, which I've abbreviated as ZXY, where X is an atom that's capable of changing oxidation state. It's capable of accepting a pair of electrons, so I've indicated the oxidation state as N. The general mechanism's got 3 stages, and we're going to track each stage through, and then we're going to map this general mechanism onto a number of specific examples of actual oxidizing agents. So the first thing that's going to happen is that our alcohol is going to react with the oxidizing agent. It's going to attack atom X, and it's going to either kick off Z, or it might simply move the electrons to somewhere else in the molecule in an addition type process. But I've shown Z being kicked out here. So what this has done is basically given us this intermediate here, where we have attached a key part of our oxidizing agent onto our alcohol. So therefore I've called this attachment, and I've ringed this in a blue box. What we now need to consider at this intermediate is the hydrogens that are attached to the carbon adjacent to the oxygen. So these ones here. Now if this is a primary alcohol, as shown here, you're going to have 2 of these hydrogens. If it's a secondary alcohol, you're only going to have 1, and this is going to be an R group. But these are the hydrogens that are going to be removed by the oxidation process. We can call them oxidizable hydrogens if you like. And what we're going to be able to do from this intermediate is push our electrons around in a circle. So we're going to start with electrons from the oxidizing agent picking up one of the hydrogens. We're going to break the carbon-hydrogen bond, and we're going to push those electrons into the carbon-oxygen bond here to form the carbon-oxygen pi bond that's eventually going to become the carbonyl. The final arrow is going to break the OX bond, and we're going to push the electrons from that bond onto X, which is going to drop the oxidation state of X by 2. So we're going to end up breaking the molecule in half. Our oxidizing agent has come off, it's been reduced in the process, and we've released something that looks broadly like our carbonyl compound, albeit protonated. So this step here, going from here to here, is the one where the oxidation level of your substrate actually changes. So the carbon here is at oxidation level 1, and here it's at oxidation level 2. So therefore I've called this the oxidation process. The final step that gets us to our final product is that we need to remove the proton from the carbonyl, and we can do this a number of ways. I've brought back Z-. So Z- could come across, deprotonate this. Similarly, we could use some electrons which are in this species over here, it doesn't really matter, or we could have an external base. But finally, this is the deprotonation step. So all of these mechanisms are going to proceed via these 3 stages: attachment, oxidation, and deprotonation. Now, attachment always happens first. We can't do any oxidation until we've attached the oxidizing agent to the alcohol. So this will always be the first step. But the other 2 can happen in either order. So we'll see some examples where deprotonation happens first before oxidation, or vice versa. Speaking of specific examples, these are 5 of the most commonly used classes of oxidizing agent for converting alcohols into aldehydes and ketones. And I'm going to discuss one specific example from each class. And we're going to map the mechanism of the specific example onto the general mechanism above, so I'm going to keep this here throughout the entire video. So the first class of compounds we're going to look at are chromium reagents, and the specific reagent that I've chosen is PCC, or pyridinium chlorochromate, which looks like this. So if we start out with our mechanism, we're going to attack the chromium atom, and we're going to kick the electrons up onto oxygen. Now, you can think of the chromium atom a little bit like a sort of carbonyl in this case, so this is similar to a 1,2 substitution chemistry. We're going to form something that's approximating a tetrahedral intermediate, although it's not tetrahedral. And we have a good leaving group attached to chromium, so we're going to push the electrons back down, kick out the chloride, and we're going to end up with this intermediate over here. Now, this has attached our oxidizing agent onto our alcohol, so therefore this is our attachment step. and that's how it maps onto the general mechanism above. Once we get to this stage, we need to identify our oxidizable hydrogens, of which there are obviously 2 still, and we can push our electrons around in a circle to remove one of these hydrogens. So the electrons come from the chromium-oxygen bond to pick up the hydrogen. We break the carbon-hydrogen bond, use the electrons to form a new pi bond to oxygen, and we break the oxygen-chromium bond, and we push the electrons back onto chromium, and this has the effect of dropping the oxidation state of chromium down from 6, which it was originally, down to 4. That's our oxidation step. The final step is our deprotonation step, and we can see that we have a pair of electrons on this oxygen up here, so we can just remove the proton here and get through to our final product, and that's our deprotonation step. So I've chosen PCC because that's the reagent that I've got the most experience with. It's probably one of the most common chromium-based reagents. But there are similar protocols. Pyridinium dichromate is a very similar reagent to PCC. Slightly more expensive, but if your substrate is acid sensitive, PDC might be a better choice. And then there's an older protocol which involves the Sarrett reagent, which is this, which is called the Collins oxidation. Collins oxidation is basically a solution of Sarrett reagent in DCM. So these are similar options for this sort of procedure. The next class of reagents we're going to talk about are activated DMSO reagents, and specifically the swooned oxidation. So in the swooned oxidation, this is our oxidizing agent, and this is what we mean by an activated DMSO reagent. You can't buy this in a bottle or anything like that. You have to generate it in the reaction mixture. So just a brief aside, it's going to get generated like this. We have actual DMSO reacting with oxalyl chloride. Basically, the DMSO attacks the oxalyl chloride. We kick the electrons up onto oxygen. Again, this is a 1,2 substitution reaction. We generate a tetrahedral intermediate. We kick the electrons back down, chloride comes off, and we end up with this intermediate here. And then the chloride that we've just kicked off comes back, attacks the sulfur, and then we kick out carbon dioxide, carbon monoxide, and chloride, and we end up with our oxidizing agent, and obviously these come off as, well, CO2 and CO come off as gases. So we've generated our oxidizing agent. So how does this react with our alcohol? Well, the alcohol attacks the sulfur, kicks out the chloride, standard SN2 type procedure, and we end up with this intermediate here. That's the attachment process done. This intermediate doesn't look too thrilled about having 2 cationic atoms next to each other. So the next step is that we've got a base in here, triethylamine. So we've added this base as one of our reagents, and that's going to do a quick deprotonation and get us through to something that looks a little bit happier. Now, we can't actually push the arrows around in a circle to remove the oxidizable hydrogens at this stage, but our triethylamine performs a dual purpose in this mechanism, in that it removes one of the protons from adjacent to the sulfur, and we end up with this species here, which is our actual active species. We can then look at the oxidizable hydrogens, push the electrons around in a circle, and that's our oxidation step. So you can see in this mechanism, the deprotonation comes first, and then the oxidation comes second, just like I said earlier. So the byproduct of this is dimethyl sulfide, which smells really bad, and that's one of the drawbacks of using the swooned oxidation. So similar protocols. The swooned oxidation is actually one of the latest developed activated DMSO oxidations, and it's based on procedures like the Fitzner-Moffat, Corey-Kim, and the Parrick-Döring oxidation. But they all operate broadly through a very similar mechanism. So the third class of compounds we're going to look at is hypervalent iodine reagents, specifically desmartin periodinane, or DMP. So DMP has this structure here, and the iodine is the kind of important atom in this one. So our alcohol is going to attack the iodine and kick out an acetate. That's our attachment procedure. We then end up with this intermediate here, and obviously the acetate that's just come off is now floating around. So we're going to use the acetate as a base to deprotonate, and we end up with this intermediate. Now, this doesn't look immediately like it can undergo an oxidation procedure, but if we draw out one of the acetate groups, we can see now how we can push the electrons around in a circle. So we can use the acetate to abstract one of our oxidizable hydrogens, and then push the electrons around in a circle as we did before. We're going to push the oxygen-iodine bond onto iodine, which is a drop in oxidation state at iodine, and we're going to kick out our acetate. So that gets us through to our final product via the oxidation step, and then our byproducts are an iodine 3 compound, where we've gone down from 5, and acetic acid as well. So similar protocols are IBX. DMP is actually made from IBX. It's just that DMP is more organic soluble, so it tends to be used a lot more commonly. Our fourth class of reagents is hypochlorite reagents or bleach reagents. Specifically, I've picked the tempo bleach oxidation for this one. So this is our active oxidizing species in the tempo bleach oxidation. And as a little aside, again, you need to generate this in situ. So this is tempo, a free radical, and by treating it with hypochlorite and a KBr catalyst, you can get through to the active N-oxo species here. So our carbonyl is going to attack the nitrogen, kick the electrons onto the oxygen. That's our attachment step. We then have carbonate in solution. So this is one of the reagents that you need to add, sodium carbonate, which is acting as a base. We're going to deprotonate this position here. That's our deprotonation step. We then look for our oxidizable hydrogens, and we find that we can push the arrows around in a circle again. So we're going to pick the hydrogen off, push the electrons from the CH bond to form the carbonyl, and then kick off the cationic nitrogen. And we end up with our aldehyde product and this hydroxide species over here. Now, this hydroxide species is regenerated into the N-oxo species by treatment with hypochlorite and KBr. So actually, tempo is just the catalyst in this oxidation, and the stoichiometric terminal oxidant is sodium hypochlorite. So although tempo is it's not expensive, but it's not cheap, bleach is obviously very cheap. So actually, the stuff that you're using up is a very cheap oxidizing agent. So the final class of compounds we're going to talk about is manganese reagents. Basically, manganese dioxide is kind of the only one that's used for this sort of procedure. You could include potassium permanganate in this category, but potassium permanganate is such a strong oxidizing agent, it basically tears molecules to pieces. So it's not commonly used in organic chemistry apart from staining TLC plates. So manganese dioxide's actually got one of the simpler mechanisms. We're going to attach our carbonyl by attacking the manganese. That's our attachment step. We are then going to look for oxidizable protons, push the electrons around in a circle. That's a drop in oxidation state at manganese from 4 down to 2. And then we're going to deprotonate as the final step to get us through to our aldehyde products. Now, the key thing with manganese dioxide, which separates it from all the other protocols we've seen, is that it's selective for allylic, benzylic, and propygylic alcohols. Essentially, the position that you're trying to oxidize, if there is pi electron density next to it in the form of an alkene or an alkyne or a benzene ring, then these will be oxidizable by manganese dioxide. Anything which does not have an adjacent pi system, so this is just a saturated molecule, won't be oxidized by manganese dioxide. So it allows you a certain level of selectivity for allylic, benzylic, or propygylic alcohols over normal alcohols. So the final slide is just a few of my observations from my experience from using these reagents, a few advantages and disadvantages that might help you in selecting a reagent to use for your particular substrate. So advantages of PCC is it's very procedurally simple. It's just literally an orange solid. You add it to the flask. It tolerates most functional groups, and it's very cheap. The disadvantage is that you're using stoichiometric chromium-6, which is toxic, carcinogenic, not very good for you. Heteroatoms sometimes interfere with PCC oxidations, and you get something called allylic transposition if you've got allylic alcohols, so they sometimes misbehave with PCC. Some people have issues with PCC with it ruining your glassware with all the chromium waste, but if you add sealite or silica to your reaction, it tends to catch all of the waste. So as long as you do the reaction properly, it's not that much of an issue. The swooned oxidation is similarly cheap. It's got excellent functional group tolerance. All of the reagents are very cheap liquids, so it's useful for very large-scale oxidations. The disadvantages are that it requires cryogenic temperatures, so you generally have to add things at -78. Also, the byproduct of swooned oxidation is dimethyl sulfide, which smells awful and is really penetrating. It'll clear out a lab in seconds. Desmartin pyridinane is procedurally simple, has excellent functional group tolerance. It's a really good oxidizing reagent. The disadvantage of DMP is it's very expensive. It's also reported to be explosive, and similarly it's made from IBX, which is even more explosive and expensive than DMP. So it's quite good on small scale, but you wouldn't want to use masses of it. Tempo bleach oxidation It's obviously catalytic, so the stoichiometric oxidant you're using is very cheap. Again, similar to swooned, useful for larger scales. Disadvantages, it's acutely pH sensitive, and you can get over-oxidation to carboxylic acids if you don't get the conditions quite right. Heteroatoms, especially ones that form hydrogen bonds, sometimes play havoc with tempo bleach oxidations. Manganese dioxide, procedurally very simple, reasonably cheap. It's selective for allylic, benzylic and propygylic, so if that's what you want, then that's wonderful. The issue with manganese dioxide is you generally need 5 or more equivalents of MnO2, so obviously you have to use quite a lot of stoichiometric excess. Similarly, it only works for allylic, benzylic and propygylic alcohols, so if you need to oxidize something that isn't one of those, MnO2 is not the best choice.